All right, let's talk about the essential toolkit for any serious Java developer. I'm talking about the 4 pillars of object-oriented programming. And trust me, these aren't just some boring academic ideas. They're the principles you're going to use every single day to build software that actually works and doesn't fall apart. I mean, we've all been there, right? You start a project, it's all clean and simple, but then it grows and grows. Suddenly, you're facing this fundamental question. How do you keep this thing from collapsing under its own weight? How do you add a new feature without breaking 5 old ones? How do you stop your code from becoming a total spaghetti mess? Well, the answer is you give your code a blueprint. Instead of just writing a giant, messy list of instructions, you start to model the real world. You create these smart, self-contained things called objects. And that right there is the core idea of object-oriented programming, or OOP. It's how we bring order to the chaos. Okay, let's dive right in with our first pillar. I like to think of this one as a safety deposit box for your code. We're talking about encapsulation. So just picture a bank account. You can't just waltz into the vault and scribble a new number on your balance sheet, right? No way. You have to go through a proper interface, like a teller or an ATM, to deposit or withdraw money. Well, encapsulation is exactly the same idea. It bundles your data, like the account balance, together with the methods that are allowed to change it, and it hides that raw data from the prying eyes of the outside world. And why does this matter so much? It's all about protection. By controlling access, you can make sure your data is always valid. For instance, you can build a rule that says a bank balance can never go below 0. It also gives you freedom. You can totally change how you store the data on the inside, and as long as the public methods work the same way, the rest of your program won't even notice. It just works. And here's what it looks like in real Java code. See that little keyword private next to balance? That's the lock on our safety deposit box. The vault door is shut. No one from the outside can touch it directly. The only way in is through our public deposit method. That's our trusted teller, and it's smart enough to check the amount first. This way, you build secure, predictable code. All right, let's move on to our second pillar, inheritance. And the best way to think about this one is a family tree. It's all about relationships and reusing what you've already built. Inheritance is super simple at its core. It just lets you create a new class that's a more specific version of an existing one. The new class, the subclass, automatically gets all the goodies from the parent, or superclass. This is perfect for modeling what we call ISA relationships. It's just common sense, right? A car is a vehicle. A dog is an animal. In Java, the magic word here is extends. That's how we build the family tree. So our car class here automatically gets the start engine method from vehicle completely for free. But, and this is where it gets really cool, we can also specialize it. We can use that @override annotation to give the car its own specific way of starting the engine, maybe one that needs a key in the ignition. Now this brings up a super important design choice you're going to have to make all the time. You have to ask, is this an ISA relationship or a HASA relationship? A car is a vehicle, so inheritance is a great fit. But a car has an engine. It isn't an engine. See the difference? For those HASA situations, we use something called composition. It's usually way more flexible, and getting this right is key to good design. And a word of warning, don't go crazy with inheritance. If you build these super deep, complex family trees, they can become incredibly rigid and a nightmare to change later. There's a famous piece of advice in programming: favor composition over inheritance. Seriously, remember that one. It'll save you so many headaches down the line. On to our third pillar, and this is where things get really dynamic and powerful. We're talking about polymorphism. To get your head around it, just think of the ultimate universal remote. Yeah, it's a big word, polymorphism. It literally just means many forms. It's the idea that you can perform one single action, but have it behave in many different ways. Think about it. You press the play button on your remote. The TV starts showing a channel, the DVD player starts the movie, the stereo starts playing a song. It's one button, but many different results. That's polymorphism. So let's see how this works in code, because this is where it really clicks. Check this out. We create a brand new dog object, but we store it in a variable that's just a plain old animal. We're treating a very specific thing in a more general way. This is the setup, the first part of the magic trick. And now for the payoff. We call the speak method on our myPet variable. So what happens? Even though the variable's type is just animal, Java is smart. At the exact moment the code runs, it looks at the actual object, sees that it's a dog, and calls the dog's version of speak. And boom, you get woof. That's the power right there. But with great power comes great responsibility, right? For all this to work safely, we need a rule. And that rule has a fancy name, the Liskov Substitution Principle, or LSP. Basically, all it means is that if you have some code that works with a vehicle, you should be able to give it a car instead, and everything should still work perfectly, with no weird surprises. So what happens when we break this rule? Let's look at a classic, kind of mind-bending example. Now, mathematically, a square is a rectangle, so it seems totally logical to model it that way. We make a new square, but treat it like a rectangle. Then we set its width to 5, and its height to 4. So quick question, what do you think the area is? 5 times 4 is 20, right? Seems obvious. Nope, it's 16. What? How is that possible? Well, think about what makes a square a square. Its width and height must be equal. So when our code set the height to 4, the square object, in an attempt to maintain its squareness, secretly changed the width to 4 as well. Our code expected one thing, and the object did something totally different and unexpected. It broke the contract. And that right there is why LSP is so critical. It's all about building predictable systems without nasty surprises. Okay, we're on the home stretch. Let's move to our final pillar, abstraction. This one is all about making things simpler. The best analogy? The dashboard of your car. I mean, when you get in your car to drive, you're not fiddling with the engine pistons or worrying about fuel injection, are you? Of course not. You have a simple set of controls, a steering wheel, pedals, a gear shift. All the insane complexity of what's happening under the hood is hidden from you. That is abstraction, hiding the messy details and only showing the essential controls. In Java, you've really got two main tools to do this, abstract classes and interfaces. And here's the rule of thumb. You use an abstract class when you have a family of related ISA objects and you want to share some common code between them. You use an interface when you just want to define a capability, a contract, like this thing can be printed or this object can fly, that lots of totally unrelated objects might need to have. Whew, okay, I know that was a lot to take in, so let's pull it all together. How do these 4 pillars actually work in harmony in the real world? Let's quickly blueprint a simple system for a library. So first we use abstraction. We create an abstract class called media item. It's a general blueprint. You can't just check out a generic media item, so you can't create one directly. Then we use inheritance. A book is a media item. A DVD is a media item. See how that works? And finally, each of those classes uses encapsulation to project its own private data, like the author for the book or the director for the DVD. And now for the grand finale. This is where polymorphism, our 4th pillar, ties everything together. We can throw all our different items, books, DVDs, you name it, onto a single shelf. We can loop through all of them, treating them just as general media items, and call one simple method, play or read. And thanks to polymorphism, Java automatically figures out which version to call. It reads the book, it plays the DVD. It just works. Look how clean and simple that is. So here's your final takeaway checklist. 1. Encapsulate your data. Keep it private and safe. 2. Use inheritance, but only for true is-our relationships. 3. Abstract your code. Program to interfaces, not specific implementations. 4. Let polymorphism do the heavy lifting for you. And the bonus tip. Always favor composition when it's a has-a relationship. At the end of the day, these 4 pillars aren't just a set of rules. They're a way of thinking. They are the professional tools you use to take a huge, complex, real-world problem and design a solution that's clean, manageable, and actually built to last. So now you have the tools. What blueprints are you going to design?